that probably take.
Hey, what's up? Coach Moore is back again. Hey, we're still solving radical equations. We're on day 2 though. I wanted to break this apart, man, so it'll be easier to digest. Yes, let's get started. All right, man. Our essential question, first of all, is how do we solve radical application problems? All right, I want to go over this warm up with you. The warm-up, guys, just consists of a couple rules that we had before. You guys need to know that the square root of x, I'm going to start with that. The square root of x can be rewritten as an exponent. All right, remember that there's an implied 2 right here, like so. All right, well, that is when you have a radical. All right, when you have a radical, this is your index. All right, this is your index. All right, or your that's your index, all right, which is your base. Your denominator. All right, and then your power, which is right here, is your numerator. All right, and I'm going to show you what I mean. If I rewrite this, the square root of x, all right, the square root of x, well, I can rewrite this as x to the 1/2. And here's what I mean. The index right here, the 2, the implied 2, is your denominator, like so. And your power is 1 right here. All right, it's your numerator. So this is x to the 1/2. All right, or let's say we had the cube root of x squared. Okay, let's use that example so you can just see another one. Well, just like this one right here that we just did. When you rewrite it, this becomes your denominator, so you have x to the 2/3. All right, x to the 2/3. Again, that 2 becomes a numerator, okay? So the cube root of x squared is x to the 2/3 power, all right? Now, remember, you can take this in reverse. Like, let's say we had x to the, let's say, 5/3. All right, well, we can rewrite that as, remember, that becomes your denominator. The denominator becomes your index, so the cube root, and then we have x to the 5th. All right, like that. All right. Or if we had like x to the 4/7. All right, then again, that becomes your denominators. The denominator becomes your index, the 7th root of x to the 4th, okay, like that. That numerator is your power, okay. Now, the reason I'm doing all that is because I just wanted to review this concept before we tackle this, okay. So what we want to do is see how this is the 1/2. Well, 1/2 is the same thing as square root, right? So how do you get rid of the square root on both sides? All right, like if this was 2x plus 15, right? Well, you would square to get rid of the square root. All right, so we do the same thing. We square this side, which means we square this side. So the 1/2 and the square cancels. All right, a squared. Now I'm going to move everything to one side. So I'm going to go minus 2x. I'm going to go minus 15. All right, so now I have 0 equals x squared minus 2x minus 15. All right, now factor this as a trinomial. All right, you're going to factor that. So that's going to be x minus 5 and x x plus 3. All right, right there. All right. Now, you set that equal to 0. You get x equals 5, and you get x equals -3, like that. Okay. Now, of course, you got to check yourself. All right. Check yourself. So we're going to take the 5. We're going to plug it in. So you have 2 times 5. Oops. 2 times 5. All right. Plus 15. All right. To the 1/2 equals 5. All right. So now you have 10. 10 plus 15 is 25. Alright. Alright, raised to the 1/2. Now, this is the same thing as the square root of 25, okay? So the square root of 25 is 5, alright, which equals 5. So this is definitely one of the solutions. Now we're going to check the other one real quick. We'll check the other one. So when we check the other one, we have 2 times -3 plus 15 raised to the 1/2 equals -3. So this is -6 plus 15 raised to the 1/2 equals -3. So -6 plus 15 is going to be 9. Alright, and 9 to the 1/2. Alright, that's going to be 3. Alright, that's 3, and you have -3. Alright, so 3 does not equal -3. That's not true, okay? So this right here is not a solution. That's why you got to check it, okay? You have to check it, alright? Now, moving along. Right here, alright, we're going to do the same thing. So this time, see how we're going to divide by 3 first. Alright, divide by 3. So we have s plus 5 raised to the 1/3 equals 3. Then to get rid of this 1/3, we're going to raise both sides to the 3. Alright, to the 3rd power. And then that cancels. So I'm left with x plus 5 equals 27. And now subtract 5. And you have x equals 22. Alright, now of course you gotta check yourself. Alright, you gotta check yourself. Alright, so what you do is you're going to go 3 times 22 plus 5 raised to the 1/3 equals 9. So 22 plus 5 is going to be 27 raised to the 1/3. Alright, 27 times 1/3 is going to be 3. 3 times 3 is 9, so 9 equals 9, so therefore this checks out, okay? Alright, so now we have this word problem. Alright, this is the application portion, guys. Look at the word problem. The formula is intact. Alright, just use it. Alright, and you will be okay. So let's go ahead and dig in, man. Look for some context information. The speed in miles per hour that a car is traveling when it goes into a skid can be estimated by this formula right here. S equals the square root of 30 feet per distance, all right? Or friction, excuse me. All right, and then D is the length or distance, okay? It says, if a speed limit is 45 miles per hour where a car goes into a skid, the coefficient of friction is 0.7, and the skid is 120 feet long. What's the driver speeding? All right, so we're gonna use this equation and we're gonna solve. Okay. It says if the speed. Well, first of all, let's address what we're looking for. It says was the driver speeding? All right, speeding. That's S. So S is S. All right. Now, knowing that, we're going to go to the right side of the equation. We know that this 30 is 30. But it tells us what F is. It says the coefficient of friction is 0.7. So F is 0.7. All right. And then the skid is 120 feet long. Well, that's D, right? It says the length of the skid, 120 feet. All right. So now, guys, we just solved that. Okay. We solved that. And when we do that, we're going to get S equals 50.2 miles per hour. So the question is, was he speeding? Yes. Yes, he was speeding. And I did all this in the calculator, man. All right, I just put that literally in the calculator and did it. All right, you can do that too, okay? Now, when we go right here, it says, how fast was the car going? Again, that's speed. How fast was the car going if the skid marks are 35 feet and the coefficient of 0.7? So again, we're looking for S. All right, we know that equation is 30 times the skid, the F, the friction, which is 0.7, and the distance is 35 feet. So again, I put that in my calculator. When I do that, I'm going to get 27.11 miles per hour. All right, so it says how fast was the car going? 27.11 miles per hour. Now, number 2. All right, so this next one, on a clear day at sea, the approximate distance D in miles that a person can see is given by this formula. D equals 1.2116 times the square root of H, where H is the person's height in feet above the ocean. So how far can a captain of a ship see when he is on deck 15 above the surface of water? So again, man, we're trying to figure out how far he can see. All right, when he's 15 feet above the water. So we go D, the distance, equals 1.2116 times the square root of 15. All right, because the height is 15. And when we do that, we get D equals 4.69 feet. Again, I just put that in my calculator, guys. All right, right here, how much further can the sailors see in the crow's nest? Is 120 feet above the water. All right, now the thing I want you to see is they're saying how much further can the sailor in the crow's nest see. So we're going to compare this answer here to this answer, because we know how far this sailor can see, or the captain, right? We're going to look at the sailor now, see how far he can see. So now we look at the sailor, okay? He's 120 feet up. We're going to find his distance, how far he can see. So we use the same equation, except we know he's 120 feet up. So we're going to go to the square root of 120. And when we do that, that's going to give us 13.27 feet. So we know that this sailor that's on the crow's nest can see 13.27 feet out into the ocean. So remember, it says how much further can this sailor see than the captain. So if I want to find how much further, then obviously I'm going to subtract. All right, that's 27. So I subtract 4.69 from 13.27, and that is going to give me 8.58 feet. All right, so this sailor can see 8.58 feet further than the captain can. Okay, and then this last problem right here, guys, it says if the pirate ship is sailing towards them at 10 miles per hour, how much sooner will the sailor see it? So remember, I don't know if you do remember, but the formula for distance is going to be distance equals speed times time. All right. So we know what the distance is. The distance is going to be 8.58, and we know what the speed is, right? That's 10 miles per hour. All right, times time. All right, we got to find time because it's how much sooner. So we got to find time. So what we do is we solve for t. Okay, so we're going to do that by dividing out 10. All right, and when you do that, you're going to get 0.858 equals t. All right, now what does that actually mean, guys? Well, if we're talking about time in hours, well, if I took 60 minutes and multiplied that by 0.858, I'll get 51.48 minutes. All right, it's time. Okay, so there you go, man. I really hope this helps you. Take it, use it, watch it again. Watch day 1, guys. We got a quiz coming up, so please make sure you take advantage of this opportunity. Okay, use your resources wisely this semester. And that's it for me, Coach Moore. I'll catch you later.